nitrate and barium chloride. Write the balance equation, what's going to happen? Go to periodic table up here so I can see it. Okay. I'll let you know. Okay, we're still going. So what's sodium nitrate?
So it'll be Na plus 1.
Right.
And then nitrate is SO.
That's sulfate. The nitrate is nitrogen.
Oh,
nitrate.
NO3, sorry.
Right, perfect. You got it. +1, -1.
Yes, so
very good. And then barium chloride.
So that'll be Ba.
Right. Right.
And then chloride is Cl -1.
Right.
So it'll be Cl +2.
Cl2.
Cl2.
And what's it going to form? The double displacement reaction.
So that'll be sodium, Na.
Na, right?
Chloride.
Perfect. What's the charges?
Chloride is, shit. Na is, I think it's like +1. Na is +1, and then chloride is -1.
Okay, that's perfect.
And then that'll be Ba. And then NO3.
Okay, then do your charges.
Ba is +2, and then
Right.
NO3 is -1. So parentheses 2.
Got it. Perfect. You're an expert at it.
Mhm.
Very good.
Thank you.
All right. Now, let's do the molecular weights of NaNO3. Figure out the molecular weights of these things. What does 1 mole of NaNO3 weigh?
NO3. Oh, we would have to separate it, right?
Right. So you go. We'll do the first one here. 1 Na, 1 sodium, 1 nitrogen, 3 oxygens. So 1 times sodium, which is 23.
23.
1 times nitrogen, which is 14. And 3 times oxygen, which is 16. So 23, 14, 32, 60, 16 times 3, 48, right? 32, 42. Yeah, 48. It's 85 grams per mole for sodium nitrate. 1 sodium, 1 nitrogen, 3 oxygens. Okay. Do the same thing with barium chloride too. When you get caught up here.
Okay.
Okay, so let's do barium chloride, same thing.
So that'll be 137 for BA,
Okay, so 1 barium. And this is 1, and barium is 137, right?
Yes, 0.3. I don't know if you're gonna.
Yeah, 137 is fine. We'll just round them off for now.
Okay. And then chloride is 35.4.
Okay, 35.5, round it up, yeah. Make it easy to do calculations. 2 chlorines. So 2 times 35.5. Comes out to 137 and 71. $208 grams per mole, right?
Yes.
Sodium chloride. Comes out to what?
Na, 1 Na,
Okay, 1 Na.
which is 123. 1 times 23. And then chloride, 1 chloride as well,
Right?
which is 35.5.
See if that's what you get here.
Okay. Okay, and then the other one.
Yeah, 58.5 for sodium chloride.
Yes.
Okay.
Yes.
The other one's barium nitrate.
So BA 1. Would that be 1 or that'd be 1, right? Yes.
Right, perfect. 1 BA.
And then nitrate, right?
Right.
1 nitrate, and then
Now, hold on.
wait.
We got to go by elements, not the compound.
2.
2 nitrogens, right?
Yes.
Okay, perfect. 2 nitrogens, and then what?
2 nitrogens, and then would that be 6 oxygens?
Yep, perfect. So BA is
Nitrate is 14.
Was 137? Yeah, 137. Nitrate was 14, you're right.
And then oxygen is 16.
16. So we have 131, 137.
Was
16 times. And 6 is, yeah, 96. So 7.
okay.
Okay.
Yes.
All right. Perfect. So we got all that. And we put everything together and doing calculations. And we were doing ones with no limiting reagents. So let's do an example one, then we'll start with limiting reagents and do examples with those. Say we're going to burn, let's do pentane gas. We burn pentane gas. Pentane is C5H12. We burn how many grams? Burn 68.3 kilograms of pentane gas. Right? Whenever we burn gas, it means add oxygen and then it produces CO2 and water. We're dealing with hydrocarbons. So we're going to burn 68.3 kilograms of pentane gas. And we want to know how much carbon dioxide is produced. So if we burn 68.3 kilograms of pentane gas, how much carbon dioxide is going to be produced in the atmosphere for greenhouse gases? Right? In excess of oxygen. So you just burn it in the air. So first thing we do is convert everything into chemistry, right? So we write our equation. So we have C5H12 plus oxygen. That's when we burn it. When something burns, it burns the presence of oxygen. We have unlimited oxygen in the air, and it produces carbon dioxide and water. So we have our equation, right?
Yes.
Okay. Now what do we do with every equation once we write it?
Balance it.
Balance it. Perfect. So let's balance this thing.
So I have a question.
Sure.
So carbon dioxide is CO2 and then the plus H2O.
Plus water, right?
Okay.
So anytime we burn a hydrocarbon like octane, like gasoline, diesel fuel, whatever the hydrocarbon is, propane, methane gas, butane gas for lighters, anytime you burn a hydrocarbon, which is carbon, hydrogen, you burn, you add oxygen, everything has to have oxygen to burn, and it produces CO2 and water.
Okay.
Like we burn sugar in our body, metabolism, glucose, it produces CO2 and water.
Okay.
Did that answer your question?
Yes.
Okay.
So carbon has a 5 in it. Can we put a 5 next to the one on the other side?
Okay, so put a 5 in front of the carbon dioxide, right?
And then hydrogen has 12.
Right.
So can we put a 6 next to the other hydrogen?
In front of the water, H2O, yep.
And then oxygen has 2. But now it has 10 on the other side. So does that mean I have to put a 5 next to this one?
It doesn't have 10. Count again.
Oh, okay. So plus the other ones. Okay.
Right. You got to have both. There's oxygen in both compounds.
So I have 16.
Yep.
So can I just put an 8?
That's what I would do. Then double check it. 5 carbons, 12 hydrogens, 12 hydrogens, 16 oxygens, 10 and 6, 16 oxygens. Perfect. Okay, then what I do, I just put all my information down here. So here's my equation, and I have 68.3 kilograms of pentane gas. I have extra oxygen, and I want to know how much CO2 is produced, and let's say in kilograms. So I want to go back to in kilograms. So how many kilograms of CO2? So everything's right there. So you got all your numbers, you got what you have to do. So we start writing our equation. Everything's right in front of you.
Yes.
Okay, so write down what we're starting with. $68.3 kilograms. And this is pentane gas. And what do I want to convert into? I want to get to grams, because from grams I can go to moles on molecular weight.
Okay.
Actually, before we start that, let's do our molecular weights. So we're going to need the molecular weight of pentane. You're going to need the molecular weight of carbon dioxide to do our calculations, because everything has to go to moles. So let's calculate C5H12. What's that molecular weight? And we'll do CO2 also. So C5H12 is 5 carbons, 12 hydrogens. Okay.
That's 5 times 12.
5 times 12, which is 60. No, 62, right?
Yes, 60.
No, 5. No, 60.
Yes, 60. And then it's 12 times 1?
Yep.
Grams per mole.
So it comes out to
72.
72 grams per mole. Okay. And we're going to need carbon dioxide also. So CO2 is 1 carbon, 2 oxygens.
2 oxygen. So 1 times 12.
Yep. So 1 is 12.
2 times 16.
Yep.
So it'll be 44.
Perfect. Okay, so we got all the information we need. So now let's start with our equation. 68.3 kilograms of propane. And I want to go from kilograms to grams. Okay, now I got the grams. Then I go grams to moles. So I know for propane, it's 72 grams per mole of propane. Okay. So I convert from kilograms to grams. Then grams, I use my molecular weight as a conversion number to go from grams to moles. I have to get to moles to use my chemical equation because it's always in moles. You've got to go to moles.
Also, it'll just be 72 grams
Per every mole.
per mole.
Right. And grams go on the bottom so they can cancel.
Oh, it's there already.
Was that?
Oh, it's already there. I rewrote it.
Does that make sense?
Yes.
Okay. And then I go from moles to moles using my chemical equation. So I went from kilograms to grams, grams to moles. Now I go moles to moles. I have moles of propane. Has to go on the bottom so it cancels. And I want to go to moles of CO2. If I wanted water, I meant moles of water. If I want CO2. And then I look at the ratio. What's the ratio of moles of carbon dioxide to moles of propane?
Is it 5 to 1? No.
5 to 1. Exactly. 5 moles of CO2 to 1 mole of propane. Those are these numbers right here. Okay, so now I have moles of CO2, right?
And then we just cross them out, or it has to keep going?
We have to keep going. We don't want moles, we want kilograms.
Okay.
This is what our questions ask us. We want kilograms of CO2. Make sure we answer the questions being asked, not just keep doing conversions. So now we can convert moles of CO2 to grams. Then from grams, I go back to kilograms. So I know for every mole of CO2 I have, it weighs how many grams? We said right here, 44. We have 44 grams of CO2 per mole. 44, I think that's 42, 44. Okay, and then from grams, I go to kilograms, right? And
yeah.
Grams, I want kilograms on top, grams on the bottom, and K is 10 to the 3. Now I have kilograms of CO2. So I have gone kilograms of propane to grams, grams of propane to moles of propane to moles of CO2, moles of CO2 to grams of CO2 grams of CO2 to kilograms. So everything cancels. And just make sure every block we have now that we used is equal to 1. Okay, 10 to the third grams is a kilogram. That's 1. 1 mole of propane weighs 72 kilograms. So 72 is the same thing as 1 mole. 5 moles of CO2 reacts with 1 mole of propane. 44 grams of CO2 per mole of CO2, and kilogram is 10 to the third grams. So everything cancels, and we multiply by 1, so you don't change your value. So let's get our calculators out. And if on the bottom divide, the top multiply. So we start with 68. $68.3. Okay, and then we'll leave the exponents till the end. 68.3 divided by 72 times 5 times 44 equals. And then we got 10 to the 3 on top, 10 to the 3 on the bottom. So those cancel out. The exponents cancel out. So we're just left with, and so it actually comes out to 208.69444. Okay, and we're good to 3 7 digits. That number is greater than 5, so it comes out to 209 kilograms of CO2. And that is our final answer. Okay, does that make sense?
Yes.
All right. Let's do one more example, then we'll add our. Well, that really, I'm gonna turn this phone off because it just keeps erasing everything if I do it that way. How do I turn the phone off completely? Just hold the power button down. Slide your power off. Okay, I think it turned off. All right. So we did that. And let's say we have, let's do one more problem like that. And then we're going to add what's called limiting reagents in a second. So let's say we have, let's do another one where we're going to mix let's say we mix potassium solid in water. Okay, so you mix let's say we mix 28.5 kilograms of potassium. Place that in water. We want to know how much hydrogen gas is produced. And what do we want it in? Let's say in liters. Okay. And we'll need to know the density of hydrogen gas. So let me just get that. So we have that. I'll give you that in the equation. Hydrogen gas. Let's look that up. Density of hydrogen gas is equal to grams per milliliter. That's what I want. Point. So density of hydrogen gas is equal to 0.0052 that was in foot pounds. 0.03136 grams per milliliter. That's part of the problem too. Okay, so there's a lot of information. If I put 28.5 kilograms of potassium in beaker water, how much hydrogen gas is produced in liters? Because gas usually measured in liters. Make sure we're still recording here, which we are. Okay, so it might stop yesterday, didn't record. All right, so what's the first thing you want to do?
Write down the problem.
Yeah, you got to convert all this word problem into chemistry. So you got to put it into a chemical formula. So I have potassium gas. Potassium is K plus water. Okay, and it's going to form. Double check, make sure I'm putting all this in the right way here. Water, KCl water, water, goes water, goes to KO, potassium hydroxide, plus hydrogen gas. Now, hydrogen gas is always what? It's always diatomic. Remember, all the gases on the periodic table, all your green letters on the periodic table, green or blue depending on the periodic table, are diatomic. So it's hydrogen with H2, or oxygen's O2, fluorine gas is F2. The only exception is in noble gases. The noble gases are not diatomic because they don't interact with each other, just single. So neon is just Ne, helium is just He, but chlorine is Cl2, nitrogen is N2, bromine is Br2. So they're always diatomic. All right, so there's your equation. Once you get a chemical equation from your English person, you have to balance it, right? So how do we balance it?
So on the other side, there's 3 hydrogens.
Right.
So can we add 2 in both sides so it's just 4? Or
yeah, you put a 2 there. Put a 2 in front of the water, and put that gives us 4 hydrogens. Okay, one potassium. And we have 3 hydrogens. We have 2 oxygens. So we'd have to put a 2 here, right?
yes.
2 oxygens. So now we have 2 potassium, and then we have to put a 2 in front of the potassium.
Next to the potassium.
Okay. So you have 2 potassiums, 2 potassiums, 2 oxygens, 2 oxygens, and we have 4
hydrogens.
4 hydrogens, right? 1, 2. Yeah, and we have 4 hydrogens. Is that balanced?
Yes.
That looks good. Okay, so now we're starting with 28.5 kilograms of potassium. And we want to know how much hydrogen are produced in liters. Okay? Everything's written down in front of us now. We have our balanced chemical equation. We have what we need. So we have to find the molecular weights of potassium and the molecular weight of hydrogen gas. We're going to need those, right?
Yes.
Okay. So potassium is just one potassium. And we look on the periodic table, and that is 39. And hydrogen has a molecular weight of 2.
2.
2 hydrogens. So 2 grams per mole.
And then oxygen?
We don't need that.
Okay.
The only thing you have is water, which is not going to be involved in our calculations, and potassium hydroxide, which is not going to be involved in our calculation. The only thing we have is potassium, and we want to know how much H2 or hydrogen gas is formed. If we want to know how much potassium hydroxide was formed, then we have the molecular weight of potassium hydroxide. If we want to know how much water we used, we have the molecular weight of water. So the 2 variables that we need to convert, we're going to have to find their molecular weights. Does that make sense?
Yes.
All right. So everything's here. So let's start converting. We have 28.5 kilograms. I got to convert that into what? You got to put kilograms into grams because our molecular weight is in grams per mole. And I have to get into moles. Okay, so kilograms go on the bottom. And then grams go on top. And there's 10 to the 3rd grams per kilogram. Okay, now I've got grams of potassium. So I want to go from grams of potassium to moles.
So that'll be 39 grams.
39 grams per mole of potassium. So far, so good?
Yes.
Okay. So from moles of potassium, I want to go to moles of what? What am I looking for?
The ratio.
Right. From potassium, I go to moles of hydrogen. I want that ratio. So I got moles of potassium on the bottom, so they cancel.
Okay.
And I want moles of hydrogen on the top. So what's the ratio of moles of hydrogen to moles of potassium?
Is it 1 to 2?
It sure is. We're having with so 1 mole of hydrogen is going to be produced from 2 moles of potassium. Now I want to go back to grams of hydrogen. I want to remember going from grams, but from kilograms to grams, grams to moles to moles, and moles back to grams of the new substance. So I know moles of hydrogen, and there's 2 grams of hydrogen for every mole of hydrogen.
And then it goes to kilograms?
I don't want kilograms, I want liters.
Oh.
So now, remember I gave you the density right here. We have the density. Density is a conversion for grams to milliliters. Remember, density is mass over volume. So it allows me to convert mass to volume. So I know in hydrogen gas, I know 0.03136 grams per milliliter. Okay, so now grams go on the bottom. So it's 0.03136 grams per milliliter. Okay. So now we've gone from grams to milliliters. And from milliliters, I can go to liters. You got to put in the units that are the request. Remember, this wanted to be in liters. We usually measure gas in liters. We always can convert grams to liters, grams to milliliters by using the density. But you have to know the density to do that. Times, and then milliliters. Milli is 10 to the negative 3 liters. Okay. So let's double check everything before we do all math. We converted kilograms, grams to grams, moles of potassium to moles of potassium, moles of hydrogen, grams of hydrogen, milliliters to liters. We've done all our conversions, have canceled, and make sure every block is equal to 1. 10 to the third is a kilogram. 10 to the 3 is a kilogram. There's 39 grams of potassium per mole. That's its molecular weight. The chemical equation, 1 mole of hydrogen is produced from 2 moles of potassium. 2 grams of hydrogen are the molecular weight of hydrogen. 1 mole of hydrogen weighs 2 grams. And the density of hydrogen gas is 0.03136 grams per milliliter. Okay, and the milliliter is 10 to the negative 3 liters. So we'll end up with liters. We do all our calculations. So, the calculator. Oh, I turned my phone on the calculator. At least I got another calculator here. See if it's charged up. Yeah, no batteries in it. There you go. Put some batteries in this one real quick. Let me just grab some batteries. Should have some right here. Oh. Somehow that phone always interferes with the internet here. Yeah, let's do this. This. All right. See if this works now. Yep. We can save it in memory how to do that. All right, so top numbers multiply, bottom number we divide. We have 28.5. Okay. Say the exponents to the length. Divided by 39. Divided by 2. Times 2. Divided by 0.03136. 0.03136. Okay, equals, and this is 23.33, yeah, 23.3025 liters. And exponents are 10 to the third times 10 to the minus 3 is 10 to the 0, which is 1. So exponents cancel. So we are left with 3 significant digits we started with, right? Yeah, 28.5. So we're good to this point right here. And this number is less than 5. So it stays the same. So it comes out to 23.3 liters of hydrogen gas. All right. So all the information just went in. If we take 28.5 kilograms of potassium, throw it in water, it's going to produce 23.3 liters of hydrogen gas being given off. It's a lot of work for just to find that out, huh?
Yes.
All right. So is all that making sense?
Yes.
Because we're going to add one more step, and that's going to be our final thing. So what we've been talking about so far, we've had unlimited resources. In other words, we put potassium in enough water to do it. If we've had excess water or we've had excess oxygen in burning things. Now, we're going to talk about limiting reagents. If we're mixing two things together, one of them is going to run out first. If you're going to make, let's give an example of limiting reagents. If you're going to make a lunch, every lunch has to have one sandwich. So it has to have one piece of meat, 2 slices of bread. Okay, so we use one sandwich. So 1 piece of meat, 2 slices of bread. What else do I want? 1 cookie. Can't spell. 1 cookie and 1 apple. Okay, so say I've got 10 pieces of meat, 18 pieces of bread, 12 cookies, and 7 apples. Now, you can make as much lunch as you want, but you're going to run out of something first, right? So if we have 10 pieces of meat, we can make 10 sandwiches. I can make 10 sandwiches. I mean, 10 lunches. Okay, if I have 18 pieces, I can make 9 lunches. 12 cookies, I can make 12 lunches because there's 1 in each lunch. 7 apples, I can make 7 lunches. Okay, at 7, we're going to run out of apples, right? Then we have to stop because you can't, because then lunches won't have apples in them. So you can only make 7 lunches. So 7 is our limiting reagent. That's the one that's going to run out first. Same thing, we mix chemicals together. If I'm burning propane and oxygen, depending how much oxygen, how much propane, one's going to run out first. That's going to be a limiting reagent. Once it runs out, the reaction stops. You can't make any more lunches. Okay? So we have to figure out which one's going to run out first. Once you figure that out, then we can do all the calculations that we've been doing. Okay, because once that limiting reagent is used up, the reaction stops. Does that make sense?
Yes.
Okay. So say, let's do a reaction. Let's do, again, let's do, I want to keep things simple at first. It'll get a little more complicated, but so let's do, actually, let's say we take hydrogen. Okay, let's say we take hydrogen gas and we react it with oxygen gas. And electrolysis, electrolysis to produce water. Okay, so I have, we'll just put it all in grams to make it easy at first. Say we have 43.5 grams of hydrogen gas, and we have 16, oops, that's not 16. 16.3 grams of oxygen gas. How many grams of water are going to be produced? So now we got hydrogen gas, we got oxygen. One of those is going to run out first. Once it runs out first, okay, the reaction is going to stop. So we got to convert everything into chemistry again, just as we've done before. So here's all our starting one, okay? So we have, let's do our formula. Hydrogen gas is H2. Oxygen is O2. And it's going to produce water, which is H2O. Okay, let's balance our equation. We have to have 2 oxygen, so put a 2 in front of the H2O and put a 2 in front of the hydrogen. So it gives us 4 moles of hydrogen, 4 moles of hydrogen, 2 moles of oxygen, 2 moles of oxygen. So we have a balanced chemical equation. Okay, so let's write in here. For hydrogen gas, I have 43.5 grams. For oxygen, I have 16.3 grams. And I want to know how much water is produced in grams. Okay, that's what I need to know. Okay, that's all information there. So we have to get everything into moles to compare it. So we have to compare how much hydrogen, how much oxygen we have. See which one's going to run out first. What's going to be our limiting reagent? So you got to convert everything into moles. Everything has to go to moles to be able to use it. In chemistry, you have to compare with moles. We're using a chemical equation. So let's take 43.5 grams. Let's do moles of hydrogen and moles of oxygen. So for moles of hydrogen, we have 43.5 grams. Now, molecular weight of hydrogen is what?
Of a hydrogen is just times 1.
Yeah, there's 2 of them. So it's 2, right? So hydrogen is 2 grams per mole. Okay. And oxygen is going to be 16.3 grams. I convert that into moles. And oxygen is 16, and it's 2 of those, so it's 32 grams. Okay, so for 43.5, let's turn this back on. So 43.5 divided by 2 is equal to 21.8, roughly. Let's round it up, 21.8 moles of oxygen. And then 16.3 divided by 32 equals 0.5. Moles of oxygen. This one's moles of hydrogen, sorry. Okay, so there's our moles of oxygen and hydrogen. Now we gotta compare those. What we do is set up a simple ratio. We choose one. Oops, turn that off. Okay, so we pick one and set it equal to X. And then we're gonna compare them. So let's pick, it doesn't matter which one we pick, it always gonna work out the same. So let's set hydrogen equal to X. We have X moles of hydrogen to 0.509 moles of oxygen. Okay. So we just, here's our 2 moles. We pick one and set it to X, make a ratio. Now the ratio of hydrogen to oxygen from our chemical equation is there's 2 moles of hydrogen to 1 mole of oxygen. So these numbers come from right here. And then another comes from those we created. So cross multiply, we get X equals 2 times 0.509. So 0.509 times 2 equals 1.02 moles of hydrogen. Okay. We'll do more of these, so don't worry. We'll just kind of get the basics right now. But does that kind of make sense how we're doing it?
Yes.
Okay, so we have 1.02 moles of hydrogen. Now look at the numbers. Do I have 1.02 moles of hydrogen? Yeah, I've got 21.8. So I've got extra hydrogen. If I have extra hydrogen, that means this is my limiting reagent. I'm going to run to oxygen first because I have extra hydrogen. Because it says I need 1.02 moles. Do I have 1.02 moles? Yes, I have 21.8 moles of hydrogen. So I have extra hydrogen. So if I have extra hydrogen, that means the oxygen is going to run out first. Now, if you would have chose oxygen for our ratio, okay, let's just prove it to be the same answer, even no matter which one we pick. So let's say we have 21.8 moles of hydrogen to X moles of oxygen. Okay, this time we're going to have oxygen be our unknown value. Okay, and our ratio again is hydrogen is 2, oxygen is 1. We end up with 2x equals 21.8. X equals, so divided by 2 is, can't do it in my head right now for some reason, but let's get this. So 21.8 divided by 2 equals 10.9 moles of oxygen. Okay, so here's our moles of oxygen. 10.9, 10.9? Yeah, 10.9. 10.9 moles of oxygen. Do I have 10.9 moles of oxygen?
No.
No, we don't. That's 1.5. So we're going to run out of oxygen first. So oxygen is our limiting reagent. So either way we do it, we come out with oxygen being our limiting reagent. So it doesn't matter which one you pick. Just set up a simple ratio once you're in moles and compare them. And then look at the numbers you have and think it and see if you've got enough or too much. If there's excess, the other one's a limiting reagent. If there's not enough, that one's a limiting reagent. So either way we do it, we're still going to get the same limiting reagent. Oxygen is our limiting reagent. We're going to run out of oxygen first. So in doing our calculation, we have to use oxygen because once the oxygen is used up, everything stops. Okay?
Yes.
So now we got to answer a question. We have point, and we already figured out how much moles of oxygen we have, so we're going to do that again. So let's set up to 0.509 moles of oxygen. Okay, so moles of oxygen. I can go to moles of, what am I looking for? I'm looking for water. And what's my ratio? There's 1 mole of water to 1 mole of oxygen. And for moles of oxygen, I can go to grams. And I know water has, oxygen is 16, hydrogen is 1. So there's 18 grams of oxygen, of water, I'm sorry, per mole of water, right? Molecular weight of water, there's 1 oxygen, 2 hydrogen. So oxygen is 16, hydrogen is 1. 16, 1 and 1 is 18. So now I've taken my moles of oxygen, converted it to moles of water. And my total answer would be grams of water, which is this is what I'm looking for right here, grams of water. So I got 0.5, multiply the top, divide by the bottom. I have got 0.509. And times 1 divided by 1 times 18.
Times 18.
Okay. So I end up at 9.16 grams of water. All right. That's as hard as it gets. That's what most of us have the trouble with. These are hard problems, but we'll go through a bunch of these and they take a while to do, but that's everything. That's everything coming together we talked about. We have to know how to go from English to chemistry, put in a chemical equation by balancing all the charges and everything. Then we have to take the chemical equation, balance it. Then we got to determine our molecular weights. Okay? Then we got to take our equation. We got to see what's going to run out first, what's going to happen with the reaction. And once you have one first, you got to do our conversions to convert that to the answer we want. So kind of tying everything we've gone over into one huge problem now. Does that make sense?
Yes.
All right, so let's do a bunch of these. And you go at 10:30 again. So we got about, what, 20 minutes or so?
Yes.
Okay, let's do a couple of these and we'll be good. I'll send you a bunch of these on emails too, and we can do those on tomorrow too, okay?
Okay, thank you.
No problem, we got all that out today. Let's say you have a factory. Yeah, let's see this. And they're burning octane gas. So the factory's burning octane gas. Octane is C8H18. Okay, they're burning octane gas. Say they burn 18.3 tons of this octane gas. How much CO2, how much carbon dioxide are they putting into the air? And then we can measure that to determine their legal limits. So in other words, you don't have to, when you're doing chemistry stuff, if they're burning this much, you can see how much carbon dioxide they're putting in, how much their filters are going to need to keep the greenhouse gases down. So we want to know how much carbon dioxide in liters they're producing, okay, into our atmosphere. Because carbon dioxide is a gas, we measure that in liters. So I'm going to need, also going to tell you the density of carbon dioxide. Okay, let's look up the density of carbon dioxide. Okay, density of carbon dioxide comes out to 0.00. Let's see the density. 0.001977 grams per milliliter. That's the density of carbon dioxide. All right, so we have everything we need. So we're gonna by how much they're burning, we see how much CO2 is being produced in the atmosphere, which determine how much they have to filter before being too much greenhouse gases into our atmosphere. So let's go back there and let's figure this out. I want to make sure I'm still recording this. Yeah, it's still going. I don't know why it stopped last time. All right, so first step is to take everything we know and convert it into chemistry, right?
Yes.
So we know we burn a hydrocarbon, which is hydrogen and carbon. What do we always produce? CO2 and water, right? When we burn hydrocarbons, and burning means adding oxygen. So let's write our equation down. We have C8H18 plus oxygen goes to carbon dioxide plus water. That's our formula, right?
Yes.
All right, so let's balance this guy. So how do we balance it?
Can we do can we put a 4 and the carbon on the right?
A 4. Why a 4?
Would that be, actually no, an 8? Sorry.
It's going to be an 8. We need one more piece of information too. I forgot to put in there. We have, let's say we have available, we have I forgot one thing. So we got 3.7 tons of oxygen that are being consumed. Okay, so now we have limiting reagent. Okay, let's balance our equation because we have to have octane and oxygen. We gotta find which one runs out first. Okay, so now we got eight CO2. Then what?
And then the hydrogens.
Okay.
So put a 9 next to the one on the right.
Right.
And then the oxygens.
Okay.
There's 9, 11. Is it 11 on the right side?
No. How many oxygens on the right?
On the right? Oh, okay. Never mind.
All right. It takes practice.
So that'll be 19?
Nope.
Oh no, it's 8 times 2.
Right.
16 plus 9. So that would be, is it 25?
25, perfect. So how do we make that oxygen say 25?
Sure. Would it have to be a ratio?
A fraction, yep.
A fraction, yes.
25 over 2. Let me say 25.
5 over 2.
Now multiply everything by 2. So this would be 2. This would be 25. That would be 16. That would be 18.
So it becomes plus 25. Okay.
All right, so now we got a balanced equation. So for octane, we have 18.3 tons. Oxygen, we have 3.7 tons. And we want to know how much CO2 in liters is being produced. So now this is all that we've got right here. All right, that's what we need. So we have to find out what we're going to use, whether we're going to use our octane or oxygen to predict, to calculate our results. Because once one of those runs out, the reaction stops. You can't keep going if one runs out. So we got to find which one of those is a limiting reagent. To do that, we have to convert into moles because we're going to compare with the chemical equation. And the chemical equations are always in moles. So we got to convert both those, the octane and the oxygen, into moles. So for, let's do octane. We've got 18.3 tons. And we got 2,000 pounds per ton. So now I got pounds. And then from pounds, I can go to kilograms. And there's 2.205 pounds in a kilogram. So we went from tons to pounds, pounds to kilograms, and then kilograms to grams. Kilo is 1,000. To catch up there. And then from grams, I can go to moles, so the molecular weight. What's the molecular weight of propane? Molecular weight of propane, we have to calculate.
Grams.
Yeah, we have to calculate how many grams per mole we have. And the grams are, we have 8 carbons. So you got 12 times 8, okay, is equal to 96 plus 18, 1 for every hydrogen, right? So 96 plus, and we got 18, is going to equal 114 grams per mole. That's the molecular weight of propane. And we do the same thing with oxygen. Oxygen, we have 3.7 tons, and it's going to be the exact same conversions. We have 1 ton is equal to 2,000 pounds. We have 2.205 pounds per 1 kilogram. And we have 10 to the 3rd grams per kilogram. And how many grams per mole of oxygen? Now, oxygen is 16 on the periodic table, and there's 2 of those. So 16 is 32 grams per mole. So that'll calculate the moles of octane and the moles of oxygen. Once you have those, we can compare the 2 to find out which one's going to be our limiting reagent. So let's calculate our moles of octane. Moles of octane is 18.3 times 2,000, okay, divided by 2.205. Then divided by 114. Equals 100, and then times 10 to the 3. Let's just do times 10 to the 3rd. So our answer comes out to 1.46, round that off, times 10 to the 5 moles. Okay, and then our other one comes out to 3.7 times 2,000 divided by 2.205. Okay, we are 10 to the 3rd, and then divided by 32. That equals 1.05 times 10 to the 5th moles. All right, so now we got moles of propane and we got moles of octane. Let you catch up there with all that.
Okay.
You got it?
Yes.
All right, now we got to determine which of these is going to run out first. So we set up a simple ratio. Let's pick which one you want to pick, oxygen or octane?
Oxygen.
Oxygen. All right, so we'll take our moles of octane, which is 1.46 times 10 to the 5. That's octane. This is oxygen is X. And then from our chemical formula, we know that octane is 2 and oxygen is 25. That's our ratio, right? 225. So we know 2x cross multiply is equal to 25 times 1.46 times 10 to the 5th. So x is going to equal, let's do this here. Let's do 1.46 1.46 10 to the 5th times 25 divided by 2. That comes out to 1.8. 1.82, 1.83 times 10 to the 6 moles of, we picked oxygen, right? Yeah. All right. So that's how much oxygen we're going to need. Do I have 1.83 times 10 to the 6 moles of oxygen?
No.
No, I don't, because I only have 1.05 times 10 to the 5th. So I don't have enough oxygen to meet the requirement. So that means oxygen is going to be my limiting reagent. Okay, so this is my limiting reagent. We're going to run that first, because to react with the octane, I have to have 1.83 times 10 to the 6. I don't have that. So oxygen is my limiting reagent. So that's what I'm going to use to find out my carbon dioxide. Does that make sense so far?
Yes.
All right, so we're going to use that number since I already did my moles now. So I have 1.05 times 10 to the 5th moles of oxygen. Right, so that's what we're going to use. I want to know how many, because that's my limiting reagent. I want to know how many moles of CO2 that's going to produce. So moles of oxygen go on the bottom. And then moles of CO2 are going to go on top. And what's my ratio? CO2 is 16. Oxygen is 25. That gives the numbers for my chemical equation, right?
Yes.
Now moles of oxygen, I can convert that into grams. I use grams to go into my density. So I know moles go on the bottom of CO2 is how many grams of CO2. What's the molecular weight of carbon dioxide?
Carbon dioxide.
Okay, go ahead and figure that one out. I'll put that in there.
Um, 12 and then 16. Is it 44?
44. Perfect. 44 grams per mole. Now I know my density of carbon dioxide, so I want to go from mass to milliliters, and milliliters I go to liters, so I want in liters, it's a gas. So I want to go to, I use the density, I have 0.001977 grams. 0.001977 grams per milliliter. And milliliters, I want to go to liters. Milliliters, 10 to the minus 3 liters. All right. So let's do our, let's check everything. Moles, okay, cancel, moles of CO2 cancel, grams of CO2 cancel, milliliters cancel, we're good there. 16 moles of CO2 to 25 moles of oxygen, 44 grams per mole. There's our density, and milliliters is 10 to the minus 3 liters. Got it. All right, let's do all our numbers and do our exponents at the end. So let's do our numbers. 1.05 times 16 divided by 25 times 44 divided by 0.001977 equals. That comes out to, let's see, I got to add my exponent still in, but 1.50 actually, times 10 to the 4th. Okay, and now I've got, go back here, I got 10 to the 5th and 10 to the minus 3. So I have to have 10 to the 2. So adding my exponents into that, I have my answer of 1.50 times 10 to the, and that was 4, and that was the 2, 10 to the 6. Right? Yeah, adding to that. And that is in liters of CO2. Okay, so 1.50 times 10 to the 6 liters of CO2.